In my third circuit, I'm using a little indicator torch there and a light dependent resistor. Now that resistor changes its value according to whether light's falling on it or not. And you will see that my indicator, my yellow signal lamp, is switching on and off very neatly according to the voltage change across that potential divider. Kirchhoff's first law, if that is 1 megohm and that is 10k, the voltage across the chain is proportional to the ratio. That is 100 times bigger than that, so the voltage there at that point there is 1.4 volts. It's about 1/10 of the supply voltage. When I increase that, the resistance lowers, and my voltage there increases. So I've got, sorry, decreases, wrong way around, decreases, sorry about that. So because I'm making that lower resistance, the voltage across there drops. As the voltage increases, the bulb switches on. So I've got a night light. I am merely changing the resistance according to the light level. And the transistor is switching cleanly. Off, on. So I can make, if you like, an automatic switch that responds to a stimulus. In this circuit, and you can try it for yourself, the light level is changing the input resistance, which is changing the input voltage, to switch the transistor on and off. It's not the cleanest of switches, but it's not bad. Now the reason that happens is I am making the transistor conduct as much current as is possible. If I click on the transistor, you will see at the bottom in the properties I've got a current gain set. Can you see that at the bottom? Is it visible right at the bottom from the back? Can you see it at the back? Good. I've got a current gain of 100. Now let's have a look at transistor gain, third line. What I'm doing here is I'm making the transistor conduct as much current as it can. We say that it's saturated. It's a term used for a transistor that's conducting to its maximum gain. If we measured the ratios, which I'm going to do in the next circuit, we would see that the ratio of that to that, that's the collector current, and the base current is 100. But there's a maximum that can reach. Let's see if we can reach it. 54, 55, 75, that's still 100. Whatever I do there, that ratio of input current to output current is still a factor of 100. Sorry about the units, that reads as 0.75 of a milliamp. There is no way you can make crocodile technology consistent. It goes to its best fit value. There's always a bit of current flowing whether you like it or not, but it's negligible. Halfway, 427 microamps, that's 0.4 of a milliamp, divided into 42 is 100. My signal lamp to conduct, let's get its conducting point. 13 milliamps is too low to actually light the bulb, but the gain is still 100. There comes a point where the current is so great it's enough for the bulb and enough for the transistor. It is therefore acting as an amplifier. Got the idea so far? It's just the principle I want you to understand, not the sums. The input current divided into output current, the collector current, gives us the gain or the amplification. Okay, let's move on to now our fourth circuit. This is the